Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to chapter 18 of the textbook. Chapter 18 is talking about passive filters. And I will divide this chapter into 3 different sections. Each section I will upload for you a different video. In the first section, I will talk about the Bode Plot. The Bode Plot will serve as a mathematical introduction that is needed and will help you a lot in the coming other sections. So there are many concepts and terms that you need to understand and you need to train yourself to work with to make sure that you can do the next sections. So let's start and look at this section. Okay, so this is chapter 18 and this is the first section of it, the Bode Plot. Here we're going to start with defining few terms and understand some plots. First of all, we will start with describe the decibel relative unit. We will check the linear logarithmic scales, the two types, the linear scale and the logarithmic scale. Then we will move to the plots and we will focus on what we call it semi-log scale. It is not purely linear, it is not purely log. So it is semi-log, it combines both linear and logarithmic scale. Third, we're going to touch on the Bode plots and we will see the actual curve compared to the approximated curves. Finally, we will touch on the transfer function. It is complex, so we will see its magnitude and phase plots. Okay, decibel. The decibel, what is decibel? The decibel is a relative unit. So it is a ratio used to express the ratio on algorithmic scale. So we are moving from our normally used numbers to the logarithmic scale. In filter response, plots and specifications are often expressed in terms of decibels. So once we're talking about filters, we have to understand decibels because all the plots and specifications are oftenly expressed in decibels. What is decibel? Decibel is defined by this equation. Decibel is referred to as dB, which is equal to 10 times log of P out over Pin. So this is ratio, and after we calculate this ratio, we will take the log base 10. So it is log base 10 of P out over Pn. Actually, there is another definition for decibel using voltages rather than power. So in the voltages, dB will be equal to 20, not 10, 20 times log V out over V. And because it is a ratio, the decibel has no dimension, so it is dimensionless. Let's take an example. The output voltage of filter is 5 volt and the input is 10 volt. Express the voltage ratio in decibel. What is ratio? Is simply this number divided by this number. So V out over Vn. So 5 over 10 is equal what? Is half. But in decibel is different. So let's see what is this in decibel. Using the previous formula, we have to put in the calculator simply 20 times log base 10 of 5 over 10, which is half. So 20 times log base 10 of half. And what is it? If we calculate it, we will find it is minus 6 dB. I want to show you something over here. So why this comes into a negative number? One of the beauty of using logarithmic scale is to expand the linear scale between 0 and 1 to a logarithmic scale. So let's write this is 0 and this is 1. This will be plus infinity. And this in the logarithmic scale will be 0 and this will be plus infinity. So this will continue all the way to minus infinity. So what we will have here is that the 0 point will be equal, the log of 0 will be equal to minus infinity. And the log of 1 will be equal to 0. So these numbers between 0 and 1 will be always negative. So this range is expanded to this range. So these values are reflected over here. And in fact, the other part, let's use another color. This part is rather than folded to this part. So if we have 10 over here, 100 will be somewhere far away here, and so on. We will have here 1, 2, 3, 4, and so on. So this is 1, 2, 3, 4. So the 10 here is equivalent to 1, and the 100 is equivalent to 2, and so on. So we are folding this right side of the logarithmic scale to be one step of linear scale to be one step of the logarithmic scale. So this is logarithmic scale and this is linear scale. Okay. Now I want to define a semi-log scale. So we used to see, I know that you used to see what's called a linear plot where x-axis and y-axis both are linear. And we've seen some plots where both are logarithmic. But here in this time, one of them will be linear and the other will be logarithmic. So in the frequency response of a system, this will be the frequency, the x-axis, and it will be logarithmic scale. And here will be the system output or value. So, and this will be linear scale. And this is the frequency. Okay. So if we do have these two plots, let me clean up the slide. We will see that on the left side, we have the actual values, the realistic values of the variables, and we can see it is curves. And we have the blue one and the red one. In the right hand side, it is exactly the same, but it is lines approximation. So the red one here is in the top, so flat and then another line decaying. And the blue one here is the one at the bottom on the right side. So it is flat and then another line and again flat. So this is what we have as an approximation, and this is the actual. So this is the actual curve and this is the approximated curves. So the Bode plot. Now we reach to the thing that we need to explain and the purpose of this section. So the Bode plot is a semi-log plot. We are emphasizing it is a semi-log. So one axis will be logarithmic, which is frequency, and the other axis will be linear, which is the value of that system response. So of a filter, so it is log on x and decibel linear on y. For example, a basic low-pass filter ideally has a Bode plot as shown over here. The slope of the basic RC or RL filter is minus 20 dB per decade. What is decade? So each step on x-axis is one decade. So moving from FC to 10 FC is one decade. Moving from 10 FC to 100 FC is another decade. So this is from here to here one decay, and from here to here one decay. And when we talk about the y-axis, each step will be minus 10 if we're moving down, dB, minus 20 dB, minus 30 dB. And when we said minus 20 dB per decade, meaning if we move one decay, we will move minus 20. So in the horizontal axis, one step. In the vertical axis, it is 20 minus 20 dB. Now, this is the actual values. In fact, if you notice here, the red one is the one that we've seen it in the previous picture, which is the ideal approximated. And the blue one is the actual value. And if you notice, it is matching everywhere except at exactly underneath the FC. There is a difference of minus 3 dB between the value here and the corner and this point. So if you want to know what is the value of this point, it will be minus 3 dB over here. Let's take an example. So if you were asked to make a Bode plot of 3 decades, so 1 decade, 2 decades, 3 decades. So this is 3 decades, 1, 2, 3. You're asked to do 3 decades of frequency. So this is frequency axis, and we have the 3 decade of the frequency. For the filter that has critical frequency equals to 34. The first step is to know what is the shape of our filter. Now, it is given that I will give it for you the shape for the time being. But in the coming sections, we have to figure out what is the shape of the filter. Now, this is the shape that we're talking about. So this one here show us the shape of the filter that we're talking about. So this is the critical frequency, and this is the corner. We have to find it out. So where is this critical frequency? It is given over 34 over here. Let's look here. So I will use this tool to show you. So if this is 10 kilo, this will be 20 kilo, and this will be 30 kilo, and this will be 40 kilo. So if we're talking about 34, it will be between 30 and 40. So I will put it somewhere over here. Okay, now I have to decide where is my 0 point at the vertical axis. So let's say that this is my 0 point at the vertical axis. So this will be 0 dB. If we move down by 20, it will be here minus 20 dB, and another 2 lines, it will be minus 40 dB. If we move up by 2, this we can write down here, it is plus 20 dB. Now, I have to find out this corner, so it is between the FC and the 0 dB. So this is the FC here. If we move up, and we will find it is this point, which is relative to 0 dB. Now, to draw this part, I have to find several points across these lines. So let's move now. I will move by few 1 decay here. So I think this is 1 decay. So the distance from here to here is 1 decay. And then I will move down by 20. So somewhere here will be my next point. Again, I have to give another point. So let's move here till we reach to this point. And I will move down by 20 dB to this point. Okay, I will change the color and I will draw with this different color. So this is 1 point, this is the second point, and this is a third point. I have to draw the flat part of it first. So this is the flat part, and then I will connect this in a straight line. I hope I can do it in a good manner. Okay, so let's see how this match with the solution. Check it out. Perfect. So in fact, it matches this curve 100%. Good. So we learned how to plot these Bode plots. To review, I want just to emphasize that we have a linear scale on the horizontal axis, and the units are decibels. So each point is the difference between each lines is 10 dB, and normally we're moving by 20. So we're going down or up by 22 lines. And the x-axis, the horizontal axis, is a logarithmic scale. So we're moving from one step to another. We multiply by 10, multiply by 10, multiply by 10. We're going back, divide by 10, divide by 10, divide by 10. So each one of these steps is called a decade. So this is plus 10, 10, 10, or plus 20, 20, 20, or going down minus 20, minus 20, minus 20, minus 20. And this one is times 10, times 10, times 10, or divided by 10, divided by 10, divided by 10. That's it. Okay, the final point is to discuss the complex domain. So the frequency response of a system is called the transfer function. And this transfer function, normally it is a complex function. When we talk about complex function, it has to be represented by, if we choose to go with the polar representation, it has to have a magnitude and phase, two parts, magnitude and phase. So if we, as we discussed before, we covered the magnitude, and this is the shape of the magnitude. And if we're talking about the phase, this would be the phase of the transfer function. So we have to understand this is the magnitude and this is the phase. The phase is started with 0 degree normally, and it will go up or down by a line, and it will flat again at minus 90 or some other degrees. In the magnitude, it will have a flat part in a certain range, and it will have a decreasing or an increasing line with fixed slope, so minus 20 dB, as we can see over here in this example.
Okay, thank you for watching. By this, we have concluded the first section of this chapter, which is talking about Bode Plot. And we have covered some mathematical concepts and tried to explain the Bode Plot concepts with these terms in it. So please write down your questions and ask it to me whenever it is possible. Thank you and see you in the next video.